I could always scoop. Okay, each mic close enough in this frame of view.
Yeah, we'll make it close enough.
Okay, I am very happy and excited to introduce you Dr. Isla Simpson. Isla Simpson's coming from us from NCAR. Isla did her master's work at St. Andrews and then her PhD in Imperial College looking at stratosphere troposphere coupling and the solar influence therein. Since then, she's had positions at Toronto and then Lawrence Doherty Earth Observatory at Columbia before moving to NCAR, where she is now a scientist too in the climate analysis section at CGD, the Climate and Global Dynamics Lab. She's got very broad interests on a number of topics that are generally related to mid-latitude circulation, but she uses GCMs of varying complexity to understand dynamics, in coupled climate variability, in current climate variability and change, to understand model biases, again, stratosphere troposphere coupling, the anthropogenic forcing on climate. She's won numerous awards, most recently two from the AMS, the Bernard Horowitz Memorial Lecture, and then this year, I think, the Clarence Leroy Meisinger Award for advancing fundamental understanding of the mechanisms of stratosphere troposphere coupling. She's published a number of really great publications, some of which I refer to for my research frequently. And finally, before you get thinking that Isla Simpson is all work and no play, she's really a fun person to talk with science, but she's also a competitive badminton player. So I'll let Isla take it from there. Today, she's going to be telling us about hydroclimate in the Southwest and projections of that.
Thanks a lot. Is this working?
Yes.
Okay. Well, yeah, it's a real pleasure to be here. This is my first time visiting somewhere in about 2 years, so it's been great to have such great conversations. So this is going to be about what we can expect for the future of North American hydroclimate, but I am going to narrow it down a little bit, and it will really be a focus on the U.S. Southwest. And so this picture here, this is a picture of the Marshall Fire, which happened at the end of last year, just outside of Boulder, which is where I live. And this is a picture taken from the Mesa Lab, which is where I work. And this fire, it affected many people that I work with. And there are a number of reasons why it happened and why it was so destructive, but almost certainly there was a role for it being very dry for that time of year. So I want to start by talking about 2020, which was, extreme for a number of reasons. But one of them is what happened in the U.S. Southwest in terms of the hydroclimate. So I'm going to spend the first few minutes here going through kind of summarizing some analysis that was in this report. So this was written together with Justin Mankin, Andy Hoyle, and Ron Fu, and some other members of this NOAA Drought Task Force, to kind of summarize what happened in 2020 and kind of place it within the context of what we expect based on anthropogenic climate change. So in 2020, the U.S. Southwest was really plunged into a pretty extreme drought. And I'm going to show you 2020 from the perspective of annual averages, so just regular annual averages here from January to December, averaged over this 6-state region of the U.S. Southwest. And so here's what the observed precipitation time series and the surface air temperature looks like over the 6-state region. And you can see that 2020 was extremely dry. It was actually the driest year on record. You can go back to the 1890s. And it was also very hot. It wasn't the hottest year, but it was one of the hottest years. And so we can ask, well, what would we expect based on our Earth system models? What are the chances of having a year like 2020? And so for this, I'm going to show you results from the CNIP6 model, 33 different models. And we'll use, for future, we'll use the high emission scenario, although it actually doesn't make too much difference on this kind of horizon out to 2050, which one we use. So these are all the individual model members simulating this historical period, and we can just take the model ensemble mean to kind of get an estimate of what the models collectively would suggest the force changes. And that's what they suggest. So on average, they don't suggest really a force trend in precipitation. But of course, there's a very clear force trend in surface temperature, which is very aligned with what's happened in observation. So I want to show you 2020 from the perspective of two fields, so precipitation and then vapor pressure deficit, which might be less familiar. So VPD is the difference between the saturation vapor pressure and the actual vapor pressure. So it's the difference between how much water vapor the atmosphere can hold and how much it actually has. And then how much water vapor the atmosphere can hold, that depends on temperature. So that's where you might expect there to be a clear impact of anthropogenic forcing on what we see. And so VPD matters because if you have higher VPD, you tend to have more evaporation if you have water available. And there's pretty clear links between VPD and wildfire. This is just one example. So this is showing for each of the years in the observational record, the burned area over the US Southwest against VPD. And note that this is not a linear scale. So it's an exponential relationship. But when you have higher VPD, you tend to have higher burned area. So that's why we kind of care about VPD, among other reasons. And so these are connected to one another. You'd expect them to be anti-correlated. So if you have a year with high precipitation, you'd expect to have low VPD because it would be a year with more water vapor in the atmosphere, and it would be a colder year as well. And then you'd expect that internal variability would affect both of these things. And of course, there's the potential for external forcing. So I'm going to run you through this diagram, and it's going to show here kind of the joint probability distribution of precipitation on the x-axis and then VPD on the y-axis. This is all going to be anomalies from the 1950 to 2000 average. So what you see here right now is just the observed data points, and these are color-coded according to the year. So we got the 1950s in the dark blue up to the 1990s in the whitish blue. And you can see this negative correlation between precipitation and VPD like we. Now here is the model-based joint probability distribution of VPD and precipitation for this 1950 to 2000 period. So it's kind of the actual numbers here, think about it's about the relative probabilities that matters. The kind of darker colors here mean you have a higher probability that a given year would sit at that location in precipitation and VPD space. And so what you see is that the observations, they lie pretty nicely within this model-based distribution for 1950 to 2000. So it gives us some hope that the models are doing things kind of correctly. Now this is what has happened in the last 2 decades. And so we're now into these yellows and reds, and you see that we've clearly shifted up towards higher VPD values. And then 2020 is kind of extreme in terms of both precip and VPD. And so we can use the model then to ask, well, what would be the chances of having a year like 2020 in terms of precip and VPD? And we'll just look at the univariate probabilities here, so those two things separately, as opposed to the joint probability. And so we could say, well, if we were in the climate of 1950 to 2000, what do the models say are the chances that we have a year like 2020? And so for precip, they suggest that it's kind of about 1 in 50 year kind of event, which is kind of consistent with the fact we've seen it like once in our observational record. But if we ask the same question for VPD, it doesn't happen in the models in the climate prior to the year 2000. And so there's like 1,700 years of simulation going into this probability distribution. Not a single one of them has VPD as high as what we've observed in 2020. But of course, climate has changed, and so we can ask that same question, but instead we can look at what the models say the climate is now. So this is the model-based probability distribution, but now centered on 2020. And you can see that it's clearly shifted up towards higher vapor pressure deficits, which is kind of aligned with what we've seen in observations. And now we can ask that same question. So for precipitation, the models say in the present climate, we haven't really seen an increased chance of having a low precip year like 2020. But now for VPD, the distribution has shifted a lot to the point that it's now possible. So it's still a really extreme event according to the models. Even nowadays, it's like a 1 in 200 year kind of event, but it's now possible, whereas in the climate prior to the year 2000, it just didn't happen. And then we can say, well, what's going to happen now in the coming decades? So this is what it looks like for 2030 to 2050. It continue to shift up towards higher vapor pressure deficits. And you'll see that the distributions also become a bit broader, and it might be because variability is changing a bit. But it's very much also because the models are diverging in their responses. So when you look at precip, there's a slight increase in the chance of having a low precip year, but that's because some of the models do predict a decline in precipitation. If we look at VPD now, by the time we're in 2030 to 2050, a year like 2020, which was kind of impossible before 2000, it's a 1 in 200 year event, now will become kind of a 1 in 10 year kind of event. And then, of course, you wonder, well, what does an extreme in this climate look like? So the models don't suggest that forest climate change has made a low precipitation year like 2020 more likely, but they suggest that a year with as high VPD as 2020 is almost impossible without forest climate change, and that will continue to increase as we move forward. So we can make this kind of prediction, but what I've shown you is glossing over a lot of complexity. For one thing, I just showed you annual averages averaged over this 6-state region of the U.S. Southwest. And our projected precipitation changes have strong spatial and seasonal variations. And so just to show you what they look like, this is the ensemble mean projections for precipitation. And in the annual mean, you can see that there's not a whole lot going on over the U.S. Southwest. But locally, there's much more going on. Seasonally, there can be more going on, for example, in the winter there. The other thing is that I just kind of took all of the models as a whole as our best estimate. I think that's what we should do if we don't have any better information, kind of prefer some models over others. But the models definitely differ in their forced responses. To just kind of illustrate that point here, I'm just showing maps like I just showed for precipitation, but here you see the agreement on the sign of precipitation change. And so where you have dark colors, there's good agreement on the sign. It doesn't tell you about the magnitude, but at least the sign they agree on. And you'll see, for example, in the summertime here, it was the summer that was really extreme in 2020. We had a failure of the monsoon. The models don't at all agree on the sign of precipitation change in the summertime. So there are lots of uncertainties here that we have to deal with. And we can use our models to make these projections, but do we really trust them? We can't trust them all because they're all doing different things. So can we try to narrow down our uncertainties somehow? So if we think about it, like what's it going to take to get our hydroclimate projections for the U.S. Southwest correct? There are many things we need to get. I'm just listing kind of the ones that I see as being leading order effects here. And these are all kind of coupled to one another, interacting. And that's kind of, it's why we need to use our Earth system models to make these kinds of projections. But we also need to have confidence in what they're doing. And so I'm going to spend the rest of the talk going over two kind of somewhat separate pieces of work, but are contributions to this puzzle. The first is about large-scale circulation change and how it's connected to precipitation change. And then the other is some newer work, which I don't know for sure actually what it's about, but it's a discrepancy in the model. I think it's related to how the models are representing land surface processes under climate change, but that's kind of still to be determined. So we'll start with the first of these. And this is actually revisiting some older work, kind of trying to see if it stood the test of time. We're attempting here to constrain precipitation projections based on what we think the large-scale circulation is going to be. So it's about the wintertime, precipitation changes, and here we're looking at the end of the century compared to the historical period. Here's the CMIP 5 and 6 ensemble means. If you dig in a little deeper and you just take some averages here over the West Coast and over the U.S. South, this is all of the different models, their ensemble mean precipitation projections. You can see a large spread there. It's larger than the spread you'd expect from internal variability alone, so there's actually structural differences here that we want to try and understand. And you also see that in going from the CMIP 5 models to the latest generation, CMIP 6, we have shifted in the south from being a slight drying on average to a slight wetting. But we've also lost a lot of that ensemble spread. Hopefully I'll convince you that we can kind of understand why this has happened, and it's because our models have improved. So the topic here is trying to constrain some of this uncertainty in precipitation through understanding what the large-scale circulation is going to be, constraining our circulation. And so it's really about the stationary waves. And so here I'm just showing the stationary waves using upper tropospheric meridional wind. This is the present day stationary wave structure. This is the future minus past difference. So you can see that in schema 5 here, in the change, we get this kind of wave pattern over North America, this kind of southerly, northerly, southerly pattern over the continent. And if we just take as an index of that response, we just take the average meridional wind change here over this southwest box. In schema 5, we had a whole load of spread in the magnitude of that change. And you can really think of this as just being a magnitude of this whole wave structure. And if we go and correlate that with precipitation change, this is what we get. This is basically the correlation between the magnitude of this wave structure and precipitation change. And you see correlations here, and that's because this is kind of an equivalent barotropic structure, so that has low-level meridional flow anomalies associated with it. And if you have a larger amplitude version of this wave structure, you have stronger southerlies bringing moist air toward the west, and stronger northerlies bringing dry air in toward the south. So in this first paper, and I'm not going to go into all the details here because it's kind of older, but I want to just kind of set the scene, is that we proposed a mechanism for this change in this wave structure. And in particular, we showed that it's really these kind of intermediate scale waves. So if you take your wave field, but you get rid of the planetary scales, and you retain only the zonal wave numbers larger than 3, you can see that that's a pretty small part of the present day climate. But it's really what's responsible for this kind of southerly, northerly, southerly pattern over North America. So you have these waves, they're kind of produced in East Asia, and they're meridionally tracked, and they're zonally propagating along the Pacific waveguide. And they're what's responsible for this change. And so we did some stationary wave modeling, and that showed that an important contributor to this is the change in the strength of the zonal mean zonal wind. In particular, you get the strengthening of the subtropical upper tropospheric westerlies. And that's what's producing this change. And so just to kind of illustrate what's going on here, I'm just showing you the average of the meridional wind over this latitude band here. That's at the longitudes that you see in the map. So you're just kind of seeing this wave structure being traced out. And if you use stationary wave theory, it tells you that the waveguide here is going to support stationary waves that have a total wave number that's less than this stationary wave. That has zonal and meridional components. It depends on the zonal mean zonal wind. It also depends on the curvature of the zonal. And so basically what we argued is that under climate change, when you strengthen your subtropical westerlies, you're decreasing that stationary wave number. And that means that the waveguide is going to preferentially support larger scales, and it's going to be less able to support the smaller scales. And so to just kind of show you that in kind of a qualitative way here, if I just plot the future wave field, the red line, you can see it's kind of stretched out compared to the black line. And so that means that by the time you're downstream here, over North America, you have this kind of southerly, northerly, southerly pattern in the anomaly. So that was our argument for why you get this structure. But then we wanted to use it to explain why we get this spread and the magnitude of the response. So we argued that models that have larger amplitude stationary waves in their present day would show a bigger change in meridional wind under climate change. So we just use kind of as a measure of the amplitude of the waves, we just use the root mean square amplitude of the waves in the present day in this box region and related that to the meridional wind change. So this is what you see for schema 5. So we've got our present day stationary wave amplitudes. And this is our change in the meridional wind. And there's a relationship in the way you'd expect that if a model has a larger amplitude wave to begin with, it's showing a bigger decline in the meridional wind over the southwest. Now this is where the real world stationary wave amplitude sits. So you can see that the models are generally biased. They have wave amplitudes that are too large. And so then there's the potential to be using this as an emerging constraint. Look at where these two things intersect to come up with a more constrained projection. And so I wanted to revisit this in this paper for a couple of reasons. So one is to see, does this still kind of hold in CMIP6? It did depend on. But I also wanted to be more quantitative about how much we can actually constrain the future. You have a lot of uncertainties here in the observations, in the relationship, the other things that are going on in the models. And so in this paper, we propose a method to kind of quantify that uncertainty. And I won't go into the details, but just kind of show you the results. But the point is we need to do better than just kind of looking at the intersect here. We need to quantify how uncertain our constrained projections remain. So here's what the raw CMIP5 response would look like. And then this is what our constrained projection would be for using this relationship. So we'd say, well, most likely, we're not going to see as big a change in the meridional wind as what we see in the raw models. There's some uncertainty here, but we can kind of rule out those models that have the really large amplitude response. We don't think that they're very likely. Now, here's what the CMIP6 models are doing. And so the relationship is still there. It's still significant, similar regression line. But you see that the models have improved, so we don't have the same amount of spread in the amplitude of the present-day stationary wave. And they're closer to the observed stationary wave amplitude. And if we now look at what the CMIP6 response in the meridional wind looks like, you can see that we have less ensemble spread in the response. And the mean response has shifted to being slightly smaller than it was in CMIP5, which is kind of aligned with our expectations based on this relationship. So this constraint on the amplitude of the stationary wave response has to do the test of time, and it can explain some of this evolution that we've seen from CMIP5 to CMIP6. But who really cares about meridional wind? I guess the question is this going to then be a useful constraint on precipitation? And that's where the uncertainties become a little larger. So this is what we would have in CMIP5. This is the correlation between the present-day stationary wave amplitude and precipitation change. So you can see that models that have larger present-day stationary waves, they show more wetting on the U.S. West Coast and more drying over the U.S. South. We'd argue that those are less correct because the stationary waves have too large amplitude. If we look at this now in CMIP6, though, this relationship with precipitation has gone away. And I don't think that's because this was wrong or a statistical fluke. It was really because we had a lot of biased models in CMIP5 that were helping us out to give us this good correlation. Now the models have improved, we can't really see that correlation. So just to illustrate that here, I'm just showing the scatter plots of precipitation change against stationary wave amplitude for the U.S. West Coast on the top and the U.S. South on the bottom. And you can see how in CMIP5 we had these really biased models helping us out to give us this significant correlation. In CMIP6, those biased models have gone away. And if we just go and take CMIP5 and eliminate those most biased models, recalculate the correlation, we'd also find that it wasn't significant in CMIP5 either. So in CMIP5, we're being really helped out by these bad models to come up with a relationship between present day and precipitation change. So in terms of trying, yeah?
Just a point of clarification, you're saying bias relative to the ensemble mean, is that what you mean by bias?
Bias relative to the reanalysis. So the stationary wave, the reanalysis is this black dashed line.
Okay,
yeah. Sorry. No. Yeah. Yeah. So to kind of quantify our precipitation changes over the U.S. South, was it ever going to be useful? I guess is the question. So we didn't do this kind of quantification in the original study, which is why I wanted to revisit it. So this is the relationship we have between our present-day stationary waves and our precipitation change in CMIP5. This is the raw precipitation responses. And this is what our emergent constraint said in CMIP5. So it would say most likely we'd see a slight wetting as opposed to a slight drying. And we can kind of rule out those models that have a really large amplitude drying over the U.S. side. Now, if we look at CMIP 6, and what we see is the models have improved in their stationary waves, but indeed we've shifted to having a slight wetting, and we have much less spread across the models, and we've lost models that have the really large amplitude drying. So for the US side, I think it was kind of a useful constraint in CMIP 5, but what it means now, and it doesn't really make sense to actually plot this constraint anymore because we don't have a relationship now in CMIP 6. But the models have improved now that it's not useful anymore. But it kind of helps us to understand why we've seen this evolution from CMIP 5 to CMIP 6. And just in the interest of time, I'm not going to show you the West Coast, but this was the region where the uncertainties were really large. Quantified them properly, we would have found that it wasn't actually a very useful constraint to begin with. So the conclusions for this part are that we can kind of understand the mechanisms behind our projected changes in the stationary waves over North America and the wintertime. And through that understanding, we can relate intermodal differences in the amplitude of the response to the present day climate and constrain future projections. And that works pretty well, I'd say, for the wave, stationary waves itself. And this relationship has stood the test of time. It's still there in CMIP 6. And can explain why the CMIP 6 response, on average, is a bit smaller with less intermodal spread. And it's because our models have improved. And they have smaller amplitude stationary waves. They're overall getting a smaller amplitude of response. So precipitation, though, over the US South, I'd say in CMIP 5, we did have a constraint, and the models have evolved in a way that we'd expect based on that constraint, leading to less drying on average and a smaller ensemble spread. Over the West Coast, though, there's a lot of other things going on, and this actually isn't a very useful constraint over that region. So we kind of need to do more of this, I think, like try and understand this intermodal spread and precipitation changes and narrow it down further, and also try and narrow it down in other seasons. So now I want to kind of switch gears a little bit, and this is going to be somewhat newer work. It's still in progress. Probably going to raise more questions than provide answers. I think it's related to evaporation and soil moisture responses to climate change, but we don't actually know for sure. So it's about vapor pressure trends over the US Southwest. And I'm concerned that our models are really getting something wrong. And it's actually more general than over the US Southwest. It's over most arid and semi-arid regions. And so I want to acknowledge collaborators on this that are listed here. So at the beginning, I started out by showing you this diagram of how vapor pressure deficit has evolved over the last decades. And recall that VPD here has two parts. Right? It has a part that's related to the saturation vapor pressure, which depends on temperature. And it has a part that's related to the actual vapor pressure, which is how much water vapor you have in the atmosphere. So I want to decompose our trends in VPD into those two parts. Looking here at trends over the last 4 decades, averaged over this 6-state region of the US South. And so what you're going to see here is going to be the actual vapor pressure trend on the x-axis, so how much water vapor you actually have. And on the y-axis will be the saturation vapor pressure trend. That'll be your temperature part. And then VPD is the difference between these, and that's given by these gray contours. So we're going towards higher VPD as you go to the top left of the diagram. So this is Era 5 reanalysis trends over the last 4 decades. So you can see that it's shown an increase in the saturation vapor pressure, which is our part that's due to warming, and then a decrease in the actual vapor pressure. And this is not very sensitive to including 2020, which was an extreme year. So that's when you get to go to 2019. Here's what all of the CMIP 6 models are doing. So each model here's a different color, and you can have multiple members for some models. And you see that for the temperature part, so the saturation vapor pressure, Era 5 is pretty squarely within the model distribution. But for the actual vapor pressure, that's not the case. So almost all of the members show positive trend in vapor pressure, while the reanalysis shows pretty big negative trend. And so if we look at the VPD, you have some members that are comparable in year 5, but they're doing it for pretty different reasons. They're giving you a high VPD trend because they have a big increase in the saturation vapor pressure, which is compensating for not having this decline in the actual vapor. Here's the CSM2 large ensemble. This is a 100-member ensemble of simulations in CSM2. And you see a similar story there, just within this one bar. This is what you get in CSM2, and the blue dots here if you prescribe observation-based sea surface temperature. So that kind of shifts your likelihood toward having lower vapor pressure trends, but it definitely doesn't get you towards what we see in observation. So our models are coming nowhere close to simulating this negative vapor pressure trend that we see in year 5 over the US side. Just to show you the seasonality of that, this is just the climatology of vapor pressure, just to kind of set the scene here. So you have most water vapor in the atmosphere in the summertime when it's warmer. There is a bias here in the model compared to the observation. That may be the actual pressure part because we're not resolving the topography fully. Not totally sure, but that's the point I really want to make here is the seasonality of the trends. So this is the trends for each month of the year. The reanalysis lies outside of the model distribution in all months of the year. The negative trend is largest in the summer, but that's also when you have most water vapor in the atmosphere. So if you look at it as a percent trend, it's pretty uniform throughout the year. The year 5 is showing this pretty substantial decline in water vapor, and the models show pretty substantial increase. So they're really separated from one another. This is the vertical structure of specific humidity trends, and this is on a sigma coordinate, so it's terrain following, averaged over the US Southwest. You see the discrepancy is largest at the surface, but it's really there throughout the whole lower troposphere. So of course the question is, do we trust year 5? It's a reanalysis product, so maybe we don't. There are reasons we might not, like the underlying forecast model could have issues. Maybe there's inhomogeneities that you assimilate different observations at different times. And so this is a map of the trends in year 5. You see this big decline in water vapor over the Southwest. And this is raw station data. So this is the ISD stations. They're mostly at airports. And you can see that they won't have those two issues, right? They could have other issues. But it's reassuring that we basically see the same thing in the raw station data. That being said, we don't see it in all reanalysis products. So this is 2 other reanalysis products, and they don't show the same level of negative vapor pressure trends that we see in these 2 data. So just to be a bit more quantitative here, I'm just showing you the trends averaged over the US Southwest. You can see that year 5 and the stations are pretty similar to one another. So in the absence of not having any reason not to, I'm going to trust the station. So I'm going to trust year 5. And they're really lying outside of the model-based distribution. So let's think about then what would lead to trends in water vapor over these last 4 decades. We have external forcing. I'm going to artificially divide that up into a thermodynamic part and a dynamic part. And then we have internal variability. So let's think about, first of all, what would we expect just based on the thermodynamic effects of rising greenhouse gases? So ignoring circulation changes for now, how would we expect water vapor to change? Well, our atmospheric moisture budget, that kind of tells us that the vertically integrated rate of change of moisture, it's really a very small residual between these large terms that are close to balancing. So we've got evaporation, and this would be evapotranspiration and the other evaporation. Precipitation, and then the vertically integrated moisture flux conversion. And so in equilibrium, we'd expect that P minus E would be equal to the vertically integrated moisture flux conversion. And over land, in equilibrium, in the annual and the climatological average, and on large enough scales, so like larger than a river catchment, you'd expect that P minus E will be greater than or equal to 0 because you can't have negative runoff. And so that means that our land regions tend to be regions where we have a convergence of moisture by the large-scale circulation. So climatologically, we have convergence of moisture into land. And now what we're doing is we're warming the atmosphere, and a warmer atmosphere holds more moisture. So let's think about like the simplest thing that could happen. And suppose that everywhere warmed at the same rate, water vapor increased everywhere, following fixed relative humidity assumption, so following Clapeyron scaling. If that happened, you'd expect that atmospheric water vapor would increase at about 7%. And so if we reach a new warmer equilibrium, where water vapor is doing that, you basically have accelerated your hydrological cycle. You'd have more water vapor being transported into land regions. You'd see an increase in moisture flux convergence. You'd see an increase in P minus E, and you'd have more water vapor in the atmosphere. But that's probably not going to happen over land. Right? Land tends to warm more than the ocean. So the regions where the water is coming from won't be warmed as much. So that increased moisture transport into land regions would probably be smaller than what we'd expect. Everywhere warming the same amount, following fixed relative humidity assumption. So then you need something else to kind of keep up with this increased evaporative demand from the atmosphere. So if you had water at the surface, you expect you'd increase evaporation. In addition, though, we could have plant physiological effects going on, and that could decline evaporation. And how all this is going to work out is not very clear. Right? That's what we are needing our models to tell us. But we think that most likely we would see an increase in water vapor, but it probably wouldn't be as much as 7% Kelvin. And if we're increasing our evaporation a lot, we'd probably see a drying of the surface soil. So kind of our leading order expectations here are maybe that as we warm, we would see increased water vapor, but not as much as Clapeyron scale. Increased evaporation if you have water available. We'd see a smaller P minus E increase than what we'd expect from Clapeyron scaling, and it might even decline if the E is really important. And we'd see drier surface soils if P minus E declines. So I want to show you now what the model does, because it kind of does exactly this. So this is going to be the ensemble mean of the CSM2 large ensemble. And this is the evolution of vapor pressure. And you can see that it's pretty steadily increasing from about 1980 on. It's not quite as much as Clapeyron scaling, but it's not too far off. This is precipitation and evaporation. So evaporation starts to increase in the 1980s. Precipitation, though, stays kind of steady, but then it starts to increase later in the 21st century. And so if you just kind of zoom in here on the 1980 to 2020 period, precipitation's kind of flat and evaporation is increasing. And so P minus E itself is then actually declining as we start to warm. Runoff also declines, but it doesn't totally balance this. We do see a drying of our near surface soils. So thinking back to our kind of leading order expectations here, the model is doing exactly what we would imagine should happen. Now on top of this, we could have dynamic changes. Changes in the circulation, whether they be forced or whether they be internal variability, that could also lead to additional changes in moisture. So if we don't ignore circulation now, we imagine, well, what would happen if we have an increased moisture flux convergence because we've changed the circulation in some way? You'd expect that would lead to an increased precipitation, wetter soils, increased evaporation, and overall more water vapor in the atmosphere. So we kind of have like those two things that could really be giving us water vapor trends. And I'm artificially dividing these all up, but of course they can interact with one another. So I want to separate our vapor pressure trends that are associated with precipitation trends from those that are not. And I'm just kind of thinking of this as like a really crude way to isolate the thermodynamic aspects of vapor pressure trends from the dynamic. So we just think about if we have a large ensemble, what would we expect for higher vapor pressure trends to relate to precipitation? Well, if we had no global warming, I think we think it would look like this. An ensemble member that's showing a positive precip trend would have a positive vapor pressure trend, and vice versa. You have some circulation trend that's giving you more precipitation and more moisture in the atmosphere. With global warming, I think we'd expect that we'd shift this whole distribution up because we have that thermodynamic impact on atmospheric wall vapor. That's assuming no forced precipitation trend. If we had a forced increase in precipitation, maybe it would look like this. If we had a forced decrease, maybe it would look like this. So that's kind of what we expect. Now let's look at what the ensemble members do for the CSM2 large ensemble. So this is after removing the large ensemble mean. So this is just the internal variability. This is the trend over the last 4 decades in each of the members. You can see that by construction, it's centered on 0. But if you have a positive precipitation trend, you're more likely to see a positive vapor pressure trend, and vice versa. That makes sense. Now we add back in the ensemble mean, so we add in the forced response. You can see that we've shifted this whole distribution up to positive vapor pressure trend because of that thermodynamic effect that's acting to increase water. This is what you get if you prescribe observation-based sea-surface. And then this is what all of the other CNIP6 models do. So it's pretty similar, right? You have a correlation between vapor pressure trend and precip trend. This whole distribution is shifted up to positive values because of the thermodynamic impact. But this is where the observations are sitting. We have a bunch of different observations here. And you can see that the Southwest has experienced a pretty large negative trend in precipitation over the last few decades. And Flavio Lehner has a paper that argues for an important role for trends in tropical Pacific SSTs in this. But even though it's extreme, it's not outside of the model distribution for precip, but the vapor pressure trends are much lower than what we'd expect. And so we have 2 possibilities here. One is that this relationship between precip and vapor pressure is wrong in the models. The other is that maybe this forced thermodynamic trend in vapor pressure is wrong. So to try and distinguish between those, I want to just take a step back here and look more globally. So far, I've just looked at the Southwest. And so this is our trend globally in Euro 5. And I'm going to now shade out here in gray the regions where the trend lies within the model distribution. So you have a number of regions, including the Southwest, that are negative, declines in water vapor, and they're outside of the model distribution. But we can account for what precip's doing too, because precip is doing all sorts of things all over the globe for mostly internal variability reasons. And I want to take that into account. So kind of illustrate what we're going to do here, I'm just taking a grid point at South Africa. This is the relationship between vapor pressure trend and precipitation trend. The observations here, they lie outside of this model distribution, whatever way you look at it. But suppose the observations were here. If you just asked, well, is the vapor pressure trend outside of the model distribution, you'd say no. But if you take into account that it's doing that with a positive precipitation trend, you'd say yes. So we're going to take this relationship between vapor pressure and precipitation, calculate the residuals from that relationship, and calculate plus or minus 2 standard deviations of those residuals, and kind of place that as a kind of confidence interval around our relationship between vapor pressure and precipitation. And so now, rather than just looking at the vapor pressure trend, we're going to say, how does this vapor pressure trend differ from what we predict based on precip, and does it lie outside this gray shaded range? And so if our observations were here, we would now conclude that they are not doing what we expect based on the model. So here on the right is now what we get if we account for what precip is doing. And so this is the difference from what's predicted based on precipitation. And many more regions jump out as being more negative. There's a couple of regions that become positive, but overwhelmingly, they're kind of more negative vapor pressure trends than what we'd expect based on the model. So now I want to divide up the planet into regions of different aridity using this aridity index. And we can divide it up into humid regions, arid and semi-arid regions, and hyper-arid regions. And if we look at these regions where the model or the reanalysis is outside of the model-based distribution, they're really this arid and semi-arid regions of the world. There's a couple of exceptions like Brazil, but almost all of them are regions that are arid or semi-arid. And if we just take all of our grid points over all of the arid and semi-arid regions, this is the probability distribution of vapor pressure trends in the models. And you see it's really unlikely that you have a negative vapor pressure trend anywhere in these regions in the model. But when you look at the reanalysis, it's like 50-50. There's a very high chance we have negative vapor pressure trends. So this is the probability of having a negative vapor pressure trend. See how different they are. And even if you take the most extreme model, which has the most negative vapor pressure trend, it still doesn't come anywhere close to what we see in the reanalysis. This is just an area-weighted spatial average over these arid and semi-arid regions. And you can see the CMIP6 models here and the large ensemble here just showing the clear increase in atmospheric water vapor. And when we look at the reanalysis, it just doesn't do that. So I guess the remaining question is, do we trust ER5 elsewhere? I've showed you the Southwest. I just want to kind of run through the other continents to convince you that I think we can. So if we look at Africa, you do see negative trends in the station here over South Africa and Morocco. Over Asia, and it's kind of Uzbekistan and Kazakhstan and Mongolia, you see negative trends in the stations. Over northern Argentina, you see negative trends in the stations. Over Spain, you do. Australia is kind of hard because there's not too many stations. But I think we can trust it. So going back to this question here, we can't look at this relationship across members of the real world, right? We just have one member. But can we use space instead? So if we look at the relationship between vapor pressure and precipitation across grid points, can we use that as our degrees of freedom here? So we can first of all just see in the models, if instead of looking across members, we look across space, do we pick up the same kind of relationship as what we see here over the US side? And that's what we get if we look across space at the relationship between vapor pressure and precipitation. Now we can compare this with what we get looking across space in the reanalysis, and this is what we get. So we don't see any indication that this relationship here is steeper in the reanalysis. What we see is that it's offset. So it seems like this forced increase in vapor pressure that we see in the models is just different in the real world. It's not showing the same level of increased water vapor. So the arid and semi-arid regions of the world seem like they're just not seeing this increase in water vapor that our models predict, or that our basic kind of thermodynamic understanding of warming would suggest. So I think we need to figure this out, because for this diagram that I showed you, in the models, this kind of temperature effect is being offset partially by having more water vapor in the atmosphere. And that's not happening in the real world. And so then what's going to happen in the future, I think, is a little unclear. So just to finish up with some summaries, because there's very much open questions here. I don't have an answer. So what could be going on? One possibility is maybe the land surface has dried out so much already that we've kind of lost that evaporative source of water. So what the models do is we warm, we have more evaporation, that satisfies the atmospheric demand for more moisture. But presumably that couldn't go on forever. You'd dry out enough that that would stop happening. And what if that's already not happening in the real world? So land model experts here have a number of suggestions for reasons why the land surface in the model might have too much access to water from below. So we're trying to look into the effects of these things to see if they can kind of push the model towards what's happened in the real world by tweaking some parameters. Another possibility is that we have plant physiological effects, and maybe they're different in the real world than in the model. That's a possibility. Could be something to do with land cover changes that aren't being represented properly. So Mark Williams did a talk a couple of weeks back, and he showed the fire's impact on runoff. I'm not sure if that's a big enough effect, but maybe it's something to consider. We know that models don't get the intermittency of precipitation correctly. It could be something about that. And it's a possibility, but I will add that if you look at offline land models just forced by observation-based meteorological forcings, they don't look any different really in terms of soil moisture and evaporation. So that makes me skeptical that this alone could be responsible. Maybe we have an incorrect representation of our runoff efficiency or its response to warming, and that's a possibility. This paper by Flavio Lerner, though, looks at the present-day biases in runoff efficiency, and models are biased, but they're kind of all over the place. We need something where all the models are doing the same thing. Well, maybe it's something about our humidity profiles right down at the surface, right? Our observations are at 2 meters height, and we're not really resolving everything down there very well. It's a possibility, but if you remember and if you trust this discrepancy is there really throughout the lower tropics. Or maybe there's some kind of global misrepresentation of atmospheric moisture trends. That's another possibility. So overall, I think more analysis is needed to figure this out. But I think it's an important one, and obviously I'm happy to hear any suggestions that any of you might have for what might be going wrong. So that's kind of the summary of where we're at with this problem. I think that's all I have. So thanks a lot for having me, and happy to take any.
We get a question from a student first. Devin.
Did you, when you went back to the CMIP 6 and looked at the reduction in those really high bias models, did you look at what they changed to get rid of those large errors? Like what did they improve?
Yeah, that's a good question, and one I've been asked before, and I have not looked. There were a few models that were really not very good. One of them was the IPSL model. Another one was, I think, NEROC. And I don't know what they changed. I think there's a high chance it could be orographic representation, or it could be the mean flow and how that kind of allows the waves to propagate and exist. But so I have not looked into it, but yeah, it's a good question. It would be good to know.
Thank you.
If it had been CSM, I would have looked into it.
Is it possible to, when you're running a model, say there's a new model, and add these constraints to it at every time step to check if they are in bounds?
So kind of like a simulation to say, okay, yeah, I mean,
that keep the bounds and we would go back and rerun that.
right, yeah, so CSM can be run with data assimilation where you could say, yeah, observations saying water vapor shouldn't be that high and bring it back. So we want to be running, free climate projections with the models to say what's going to happen over the coming decades. And so while that would be a fine approach to just simulate now, I think it's not going to be adequate for getting the processes right to simulate the future. But I think maybe what you're getting at is that doing that kind of a simulation, I think, could help us understand where things are going wrong, because it would say, you need to add these tendencies to bring it this way on these kind of days or something. And then you could start to dig into it by looking at those kind of analysis increments. We have that with CSM, but it's kind of a short record. I think it runs from, I think it's like 10 or 15 years of reanalysis with CESM. So it's worth looking at, but it wouldn't be possible to look at the trend.
Okay, that just stole my question, which was, could you compare the data assimilation from error 5 with the analysis increments to see how it's pulling it back? But
Yeah, no, let me show you the slide. Yeah, so,
oh yeah,
so this is where, yeah, it gets confusing. It's very hard to know what's going on. So this is our vapor pressure trends. These are the trends in the analysis increment. And it's kind of, this is an era 5. It's kind of yes and no, right? There's quite a lot of regions that show negative trends. These lots here in Asia, where you see negative trends in the analysis increment. The analysis is constraining it to be more negative than the model would have actually proven time. But that's not really true for the U.S. Southwest. But the U.S. Southwest, era 5 is a pretty big precipitation problem. It's also not true for like South Sudan. It has a pretty big precipitation bias there too. So I think era 5 is getting these negative trends for two different reasons depending where you are. The more reassuring one is where it comes in from the analysis increment. You know, it's being constrained by observation. The less reassuring one is where it's coming in association with the precipitation bias. But that could be because the assimilation saying, oh, you need to be drier, and the only way the model can handle that is by giving you a decline in precipitation. So I don't really know what to make of this, but the answer is in some regions, yes, the increments are making it drier, but it's not true everywhere.
Brad.
I don't know, along the same line, is it possible, you showed good agreement with surface, and it may be that those are the things that are constraining era 5, and do you have, can you get any of the soil moisture analysis or the soil moisture from the SIPs to see, it may be that the land surface model is behaving poorly in all of them, right?
Yeah, so, yeah, thank you for the
And
first
the
point.
only way they can fix things is by adjusting precipitation.
Yeah. So yeah, it's definitely true that the reanalysis and the stations are not independent of one another. So it's possible there's an error in the stations that can't be ruled out. I
Or
have,
just that the analysis is being strong constrained by the station.
yeah. Sorry, I have a lot of extra slides, but okay, here. So the reanalysis does have much stronger negative soil moisture trend, which is what you see in the gray here. And it has much stronger negative precipitation, evaporation trend. So that would be a nice story. It all hang together. You'd say, okay, something in the assimilation is making the soil moisture dry out more in the reanalysis. You have less evaporation, and therefore you have less water vapor in the atmosphere. But if I show you maybe this, no, sorry, too many extra slides. The thing that's concerning, though, is that if you look at precipitation trends, this is over the arid and semi-arid regions of the world. So red is the model, black is the reanalysis. So era 5 shows this big decline in soil moisture, big decline in evaporation. But it's also showing this decline in precipitation in the blue here, which you don't see in other observation-based precipitation products. So I'm reluctant to conclude anything from era 5 other than the water vapor, because we can see that in the station, because they have this biased artificial trend in precipitation. So I think we need other soil moisture and evaporation products. And we may be constrained to looking at higher frequencies to try and see, can you see something going wrong on like daily timescales that you can then extrapolate out? So we don't really have soil moisture measurements going back to 1980. There's one European data set, which I haven't looked at yet. I think it's some kind of merged satellite thing. And then there's like SMAC, which is a few years, maybe 10 or 15 years. And so while we can't look at those trends, I think we could look at higher frequencies to see But I'm just skeptical and looking at anything in year 5 beyond what we can also see in the station because of this issue with what the precip is doing.
Year 5 have GPM in it, the global precipitation mission.
It doesn't assimilate precip. Area 5 doesn't assimilate precipitation in general. Right, Area 5 would assimilate water vapor, but not precipitation. Okay, let's get one more quick question and then we'll call it a day. Greg.
Well, it's fairly well known that there's a hypersensitivity of precipitation, much more to how dry it's getting, much more in arid climates than there is in other places. Because arid climates tend to be dependent on some kind of a mesoscale organization, which is often missed in global models. So, you know, they say the difference between a drought and a good year in some of these arid regions is just one mesoscale convective system. And if you're not really representing this balance and you're trying to distribute over something unrealistic in a global model, then that lack of suddenly shutting it off just because you don't have quite enough to organize a mesoscale system might make that difference. See what I mean?
Yeah. Yeah, I could see that being a possibility. I guess a couple of things though, and I'm not sure if that argues against it, but if you look at the distribution of precip trends, they're not different between observation and model. So it's not like precip is declining. But it's certainly possible that there's some feedback. I don't know, some runoff, precip, and evaporation are just not in the same kind of balance.
You've probably seen this in Colorado, that, you know, a wet year versus a dry year. It doesn't seem that much different. It's just that you missed one of those systems.
Yeah.
And, you know, how does a global model that doesn't even resolve fine scales, how does it even represent that?
Yeah, it's definitely, yeah, up there as one of the candidates. The only thing, yeah, there's two things that make me concerned as to whether that's really the answer. One is that overall precip declines are not different. And the other is that if you force the land model with observed precip, which presumably has these storm systems in it, trends in soil moisture and evaporation are not that different. And they're very, very similar between the pooling components. But it's possible that it's a combination of things. Right?
Yeah.
Not getting that, plus not having runoff represented correctly.
It's all threshold driven rather than continuous.
Yeah. Yeah, yeah, it's a good suggestion.
Let's thank Isla once more.